So, despite being called linear programming, there is no programming involved. No computer science programming or anything. What this essentially is taking real world problems and converting them into inequalities and finding an optimal solution to maximize profits or minimize costs or whatever. They're all about maximizing and minimizing stuff. We're going to be drawing diagrams that look like this. So if you're drawing inequalities from equity stuff and shading in bits, it's this sort of stuff that we're going to be doing. But I need to start off with how to formulate these problems, which is sometimes what they'll ask you to do in the next. So how to take the real world context that they give you and convert that into some equations. To be honest, actually, I think this is the hardest part of the pack. So after this lesson, it will get a little bit easier. So in your pack, you have space to fill these in. So some terminology that we're going to talk about. So linear programming problems are quite often about like companies and stuff making a few different types of things, and they've got restrictions on, you know, how many they can produce in a certain time frame and the materials that they've got and things like that. Okay. So the example that it gives here is about a company which makes both CDs and DVDs, which will be out of business by now. But they want to make the number of CDs and DVDs which gives them the maximum profit they can. So we'll talk about decision variables. These are the things that can be varied. These will be the number of CDs and DVDs in this question. Quite often we'll talk about the objective function. So the objective function is essentially an expression with the quantities that we want to optimize. So in this case, it's the profit, maximum profit, but could be minimum cost or other things like that. We'll talk about constraints. So these are going to be the inequalities that govern these sorts of problems. So this is, you know, I can only make so many DVDs in a day, or the maximum number of CDs and DVD I can make is 1,000 or whatever. These are the restrictions that you have on your variables. And then optimal solution is what it says on the tin. It's the best solution that we can have that satisfies the objective function. We're going to be taking real world problems, writing down some inequalities, some constraints based on and then looking for a way to optimize this, find the maximum profit, minimum cost. We're just looking here at what's the formulating the word. We're looking just here at formulating linear programming problems. So these are things that you need to do in formulating a linear programming problem. First off, you need to define what your variables are. It's easy to just jump straight in and just start writing letters and you think it's obvious, but there will be marks for defining decision variables. You need to state your objective function. So state whether you're maximizing or minimizing something and state what that equation is that you are maximizing or minimizing. And then take the information from the question and write some inequalities. These are all things that you need to say. And the first two especially are really easy to forget to do because the inequalities are the hardest bit. So let's look at an example. They all tend to be about food. Let's make so this first one is about making cake for a sale. Okay, so you've got it in your pack with a nice picture of this cake. So here's the information that we've got. It takes 30 minutes to make a cheesecake. It takes 20 minutes to make a batch of chocolate bridge cake. We've got a maximum of 8 hours to do this. We've got 20 tins, so we can make a maximum of 20 cakes. And we make £4 profit on a cheesecake and £3 on a batch of chocolate bridge cake. And we have to turn all of this into some mathematical equation. It doesn't explicitly say in the question, but we're looking to maximize profit in this case. So the first thing we're going to do is we're going to define our decision variable. So you could call them whatever letters you like. You could use C for cheesecake and F for fridge cake or whatever. But we're going to call X to be the number of cheesecakes and Y is the number of batches of chocolate fridge cake. Do you remember it should be number of, it's not just X is cheesecakes, Y is fridge cakes. So define those first. Then we're looking to state what the objective function is. So the objective function is going to be about the profit. So this is going to be taken from the profit of £4 on a cheesecake and £3 on a batch of chocolate fridge cake. Okay. We are looking to maximize this profit. So make sure you state that we're maximizing the profit. And then we're looking for an equation for how much profit we make. So we're going to make £4 times the number of cheesecakes that we make, which is 4x. We're going to make £3 times the number of fridge cakes that we make, which is 3y. So the total profit is going to be 4x plus 3y. So state that you're going to maximize, use a letter for profit, so P equals 4x plus 3. We're going to be looking to use all the information that we've said in this question so far. So we've used the profit bit down here. What we haven't used is the stuff about the timing and the stuff about the number of tins. So that's where we're going to get some constraints from. That's where we're going to get some inequalities. So let's think about the time first. We're going to work in minutes. So our units need to be consistent. So we've got minutes in here or hours. I mean, as long as you're consistent, it's fine. But I'm going to work in minutes. So the total time that we spend making cheesecakes is going to be 30 times the number of cheesecakes, so 30x. The total time that we spend making fridge cakes is going to be 20 times the number of fridge cakes, so 20y. And so the total time we spend baking cakes is adding those up. 30x was 20y. That has to be less than 8 hours or whatever 8 hours is in minutes. It's 480 minutes. So the inequality that we have is 30x plus 20y is less than or equal. You can simplify that. Obviously, you can divide it through by 10. So you can leave it as it is, or you can write it as 3x plus 2y is less than or equal to 48 units. Final bit of information that we haven't used in this question is about the 20 tins. So the 20 tins is to do with the maximum number of cakes that we can make. Well, the total number of cakes that we can make is x plus y. That has to be less than or equal to 20. We could have 20 cakes. But other constraint is x plus y is less than equal. Okay. But it's about taking every bit of information that you are given in the question and converting that into some information, whether it's an objective function, whether it's a constraint. So this is summarizing what we've just done. You don't need to copy this down. We've already just written this. There's 2 more constraints added on the bottom there, which are worth putting on. So it's kind of obvious, but you can't make negative numbers of cakes. So put on x is bigger than equal to 0 and y is bigger than equal. Let's look out for that. And that's our linear programming question formulated. We haven't actually gone on to do any solving of it. That will be a couple of lessons. But sometimes literally questions in the exam do ask you to do this. It's an important skill for you to have. Any questions on it? Yeah.
Is the number of cheesecakes you made or the number of batches? So okay, that's all right.
Right, there's one for you to have a go over the page. Give me a couple of minutes and nothing. So define your variables first. So A is number of eggs, artichoke, B is number of eggs, B is number of eggs, cabbage, all that.
Would you have to describe these constraints? Like, would you lose marks if you didn't put like land available?
No. You don't need that. As long as you've got the constraint.
Yeah. And for no more than 10, why is that equal to? For Astro.
No more than 10, so it can be equals. It can't be more than 10. Could be 10, could be 9, could be 8.
Yeah.
The objective function comes from the profit. So 500 plus 100 equals 200C. I think there's a problem with the solution in there. What's the problem with the solution?
Would have 0 as well, actually, couldn't you?
Oh,
That's much more.
it could do. Non-negative, okay. It hasn't said whether they're maximising the profit on.
It does say it wants to make as big a profit as possible. It doesn't say that. Exactly what's one.
Yeah, no, in the solution, in the question, it says he wants to make a big profit. Fine. In the solution, it just states the objective function. It doesn't say whether you're maximising or minimising, and you do need to say that. Okay, so make sure it says maximising profit. Land available is total area of land is 20 acres, so less equal to 20 per acre. See, got restrictions on article feet. Make sure you're careful with the equal to. The confusing ones, I think, are always the ones where it's like there must be at least 5 more acres of cabbage than beet. I always think that's really awkward to get the right way around. You might want to think of it like guess which way it is, and then you might want to think of an example to see if it works. So what does it say? There must be at least 5 more acres of cabbage than beet. So I think so the number of acres of cabbage, C, I think has to be bigger than beet plus 5. Is that right? Yeah. So that's the way I would do it. Okay. So it says there must be at least 5 more acres of cabbage than beet. So you take the amount of beet, you add 5 to that, and that's what your cabbage is, or bigger. So I would put C is bigger than or equal to B plus 5. But you might want to think of an example. So you might want to think, well, if there were 5 acres of beet, there has to be 5 more acres of cabbage. So there'd have to be at least 10 acres of cabbage. Does that fit with what I've put in there? You can adjust accordingly. Okay, but I think those are the hardest ones to come up with. And non-negative constraint as well. All right. So there's a lot going on in this one, a lot of information that needs kind of summarizing. So a good idea might be to put it in a little table or highlight it. So we've got 2 types of syrup, syrup A and syrup B, blending sugar, fruit and juice. It tells you the percentages of each of the syrups, which is worth jotting in your table here. Okay. It also tells you how much each litre of syrup costs. So we've got syrup A, it's 50p per litre, syrup B is 40p per litre. And it also tells us the restrictions on the maximum production of each syrup, which we'll summarise in this table here. Then we've got a confectionery manufacturer placing an order for 60,000 litres of syrup with these restrictions on the constraints. So we've got total amount is 60,000. We've got less than 25% sugar, and it's strictly less than, not equal to 25. We've got at least 40% fruit, so that one could be 40%, so that'll be bigger than or equal to 40%. And for juice, we've got no more than 35, so it's less than that 35. It could be equal to, but just no more than that. So we summarize that in there. And this is where we're going to get our constraints from. Okay, so first thing to talk about is the objective function. So we're looking to minimize costs this time. So make sure you say minimize, make sure you get an expression for the cost. So it's going to be 50p times x. Did it say x in the question? Yeah, you've already had x and y defined for you in the question, so you don't need to do it. So it's 50p times the number of liters of syrup A, which is x, plus 40p times the number of liters of syrup B. Equally, if you did it as like 0.5 and 0.4 and did it in pounds, that's fine. That's our objective function. Then we're going to get constraints from each of our bits, each of our columns from here, basically. Okay. So for the sugar, we know that 30% of the syrup A, so number of liters of syrup A, which is x, is sugar, and we know 20% of the blend syrup B is sugar. So the total amount of sugar that we have is 30% of x plus 20% of y. Okay. That has to be less than 25% of the final blend. So the final blend is your x plus y, is your number of liters of A plus number of liters of B, and 25% of that. And by the way, I think this is a really, really hard example. Okay, so this is from this first column here. So 0.3x, 0.2y, less than or equal to 0.25 of the total x plus 1. And we're going to do the same for the fruit and the juice as well. Oh, it turns out if you simplify this, you just get x is less than y. You can just write that down. Let's do the same for the fruit. So we've got 50% of x plus 35% of y. This time has to be greater than equal to 40% of the total blend. So greater than equal to 40% of x plus y, which again, you can simplify. This time turns into 2x. 2x is greater than or equal to 1. And we can do the same for the juice column. The 20% of A plus 45% of B has to be less than or equal to 35% of the total, which if you expand and simplify, gives you 2y is less than or equal to 3x. We've got some restrictions on the amount that we can make as well. So just looking at x, it has to be less than 40,000, and you can include the non-negativity in there as well. So it has to be bigger than or equal to 0. Then for y, so that has to be less than 45,000 and bigger than or equal to 0. And for the final blend, we know x plus y, the total number of liters that we use, has to be less than or equal to 60,000. So greater than or equal to 60,000. It's greater than or equal to 60,000 because the manufacturer, the order that's come in, they want 60,000. Theoretically, you could make more than 60,000 and just send them 60,000. Why would you? But it should technically be an inequality. It should be greater than or equal. I think that makes no sense. But there's a lot of information to process here to put into a lot of different inequalities. I think this is a challenging one. Any questions so far? Well, I think we've got to go. That's what we're going to do today. Again, that's food. I always got food close. Again, you might want to take your highlight to this, highlight the pockets information and stuff. But this is talking about 3 types of cakes: apple cakes, banana cakes, and cherry cakes, conveniently chosen to fit the letters A, B, and C. First thing we're going to do is define what A, B, and C are. So part one says the availability of flour leads to this constraint. Thankfully, we don't have to work that one out. But it says give the meaning of the variables A, B, and C in this constant. So A is going to be the number of apple cakes baked. B is the number of banana cakes. C is the number of cherry cakes. That's defining your decision variables to start off with. It then wants us to do a similar thing to come up with a similar constraint for sugar. So let's talk about where the flour comes from first. So this constraint for the flour has come from the second line where it talks about the baker having exactly enough flour to make either 30 apple cakes or 20 banana cakes or 40 cherry cakes. Importantly, it's exactly enough flour. Okay, so the total whatever of flour, number of kilograms or whatever of flour, has to be divisible by 30, 20, and 40 because it's exact. Okay. You could choose a sensible number that is divisible by 30, 20, or 40. You could choose 120. You could choose 1,200. There are other options you could have. But let's just choose 120. So we're saying the total amount of flour has to be less than or equal to 120. The amount of flour used. All right. Let's think about then if we were just making apple cakes. So if we were just making apple cakes, okay, we've got enough to make 30 apple cakes. That would require us to times that by 4. 400 grams would be more sensible than kilograms. So I'm going to say that if I was just making apple cakes, that would be, so number of apple cakes times by 4, because I can make 30 of those apple cakes. Okay, so assuming we make no banana cakes, no cherry cakes. Let's do the same thing for banana cakes. So assume we only make banana cakes. We can make 20 banana cakes out of that flour. So that is times that by 6. And the same for cherry cakes. If we can only make cherry cakes, we can make 40 cherry cakes. That's times that by 3. Okay. So these are kind of the maximum things we can have for apple cakes, banana cakes, cherry cakes. Don't pull that face at me. I can explain it another way, but I'm not sure it makes it any better. In terms of the constraints, then you'll have lots of different numbers of banana cakes and cherry cakes that you can make. Okay, so just put pluses in those, and that's where that constraint comes. We can do the same thing for the sugar. So for the sugar, we've got exactly enough sugar to make 30 apple cakes, 40 banana cakes, or 30 cherry cakes. So again, I'm looking for a number that goes that is exactly divisible by 30 and 40. So 120 works for that as well. Or 1,200. Just looking at the apple cakes then, suppose we only make apple cakes, we can make 30 of them. That is times by 4 again to get that maximum.
Why is it less than or equal to?
Because we don't have to use all of the flour and all of the sugar. We've got enough flour to make that. That's the maximum that we can have. But technically, we don't have to use it all. We could use less. Then thinking about banana cakes, suppose we make the maximum of banana cakes we can have, which is 40. How much sugar would that be times by? So that would be times by 3 sugars. 3 sugars doesn't make sense. And same for cherry cakes. Maximum number of cherry cakes is 30. What would that be times by to get 120? That would be 4 cherry cakes. I think you can understand that as kind of the most straightforward way of coming up with these inequalities. Thinking about if you only made that type of cake, what's the maximum? I can explain it another way, but not today. If you want it. So the way it does it in the thing is does it with 1,200 instead, but does the same thing and comes up with that same constructor. I think that's the hardest bit. So the next bit is formulate linear programming problem. So first off, let's state the objective function. We're looking to maximize profit. Profit that we make is 4p per apple cake, so 4 times the number of apple cakes plus 3 times the number of banana cakes plus 2 times the number of cherry cakes. I think worth it. Bakery business. We've got our 2 constraints from earlier on in the question. We've got both of those. We have enough apples for 20 apple cakes, so the number of apple cakes has to be between 0 and 20 with that non-negative. We've got enough bananas for 25, so B has to be between 0 and 25, and enough cherries for 10, so C is between 0 and 10. Equals to
No. Yeah.
You can make me up. You get the LPM. Finally, we've got an order for 30 cakes. So the total number of cakes has to be less than or equal to 30. So A plus B plus, oops. A plus B plus C has to be less than or equal to greater than or equal to 30, not less than or equal to 30, greater than or equal to 30, because it's a minimum of 30 cakes. They theoretically could bake more cakes and not sell the filling. But why would you? But technically, because it's greater than 30.